Hello and welcome to our session number 35. In today's session we're going to be finishing up, it's about time, the metal oxide semiconductor structure. And next session we'll be going on to the metal oxide semiconductor field effect transistor, the MOSFET, and we'll be spending quite a bit of time on that. Anyway, in today's last section on the MOS, we'll be looking at the CV plots, the capacitance voltage plots, and we'll be using the theory that we developed in our last session. And then we'll be going on to looking at the Debye length, a few words about a very interesting person by the name of Peter Debye. And we'll be applying that not only to semiconductors, but to plasmas. And we'll be ending up with a closer look and discussion of the Debye length, and ending with I think what you'll find is a very beautiful performance of Mozart. But to get us started, let's go back, turn the clock back to 1887 on a showboat on the Mississippi River. We're going to be listening to Lola and Julie and Joe and Queenie as they sing "Can't Help Lovin' That Man of Mine." And the performance is from a marvelous show, 1989 paper mill production of Showboat. And we'll see you back in about 6 minutes.
Julie, he said he liked me. Do you think he meant it?
I don't know, child. I don't know as I like you to go fall in love with some man that nobody ever heard of. Well, suppose he turns out to be just a no-account river fella.
But if I found he was no account, I'd stop loving him.
Oh, no, you wouldn't. Once a girl like you starts to love a man, she don't stop so easy.
Well, couldn't you stop loving Steve if he treated you mean?
No, honey. No matter what he did.
Why do you love Steve?
I don't know. He's such a bad actor on the stage, and he thinks he's so good. Maybe that's why I love him. Oh, you see, child, love's a funny thing. There's no sense to it. That's why you gotta be so careful when it comes creeping up on you.
It's like that thing you always sing when we take our walks.
Yes, I know. Fish gotta swim, birds gotta fly. I gotta love one man till I die. Can't help loving that man of mine.
That's it.
How come y'all know that song?
Why? Do you know it, Queenie?
For sure I does, but I ain't never heard anybody but colored folks sing that song. Sounds kind of funny for Miss Julie to know.
Why, Julie sings it all the time.
Well, can you sing the whole thing?
Oh, well, of course I can. What's so funny about that? Oh, listen, sister, I love my Mr. Man, and I can't tell you why. There ain't no reason why I should love that man. It must be something that the angels done plan. Fish gotta swim, birds gotta fly. I gotta love one man till I die. Can't help loving that man of mine. Tell me he's lazy, tell me he's slow. Tell me I'm crazy, maybe I know. Can't help loving that man of mine. When he goes away, that's a rainy day. I
Miss Julie.
Was that you, Miss Julie? That's my favorite song.
My man is shiftless and good for nothing too. He's my man just the same. He's never around here when there is work to do. He's never around here when there's work to do. The chimney's smoking, the roof is leaking in, but he don't seem to care. He can be happy with just a sip of gin.
Why you all talk about gin?
I even love him when his kisses got gin.
Well, look at that gas shopper.
Slowly.
Okay, welcome back. These are some of the topics we'll be covering today. There aren't too many of them. We generally have a few more, but these are serious topics. So we're going to have hopefully a lot of fun, and we're going to go into these topics in some detail. We're going to start off. Basically, I'm saying that we're going to divide the session into two parts. One, we'll be looking at the capacitance voltage or CV plots quantitatively, so that'll involve a little bit of mathematics. And then we're going to be switching over to looking at a related topic called the Debye length, and we're going to see how it applies also to plasmas. We're going to take a closer look at it, and we're going to end up with a summary and discussion of the Debye length. So let's get started. Okay, so this is a general simple model, quote-unquote simple model, for a p-doped silicon substrate, or NMOS. We know it's NMOS because even though there's symmetry on the left and right sides, the middle part is not symmetric. This is a typical kind of structure, curve that we would have for depletion. And this clearly is not symmetric. So just inspecting this thing, we could say, this must be an NMOS. And if it's NMOS, the flat band voltage is on the left side, and the threshold voltage is on the right side. If it was PMOS, or an N-type silicon substrate, then it would be just the mirror image. This thing here, instead of bending like this, it would bend the other way. Okay, good. So again, we define three separate regions in the simple theory: accumulation, where the substrate is more p-type. We have depletion, where we start to repel holes and we start to uncover fixed negative ions, because the ions in p-type silicon are negative. They are arsenic. They've accepted an electron. They become negative ions. Somewhere in this region we have intrinsic, not shown in the simple theory. We get to a point where we have so many, we start to, somewhere in here, we start to attract electrons to the oxide silicon substrate. And when we get to the point where, let's say, the substrate is doped 10 to the 17th, we get 10 to the 17th at the interface. The interface, or the surface, is shielded, and all of a sudden, at this point, if we increase the gate oxide, make it more positive, then all of the electrons are attracted to the surface, and the depletion region stays at its maximum width, WD max. And then the capacitance jumps up, and we get Cox, just like we had Cox for accumulation. So Cs is an areal capacitance in farads per square centimeter. Well, how do we use the theory that we developed in the previous session to figure out what these different capacitances are? The depletion capacitance, the flat band, and the threshold. All these things we can get from the theory which we've already developed. And this is equation 1820. It's repeated as equation 1830 for the surface charge, and there are 6 terms for the surface charge. But there's only, actually remember we had 4 terms for the electric field, and we integrated, we would have 4 times 2 because there's a lower level of integration and an upper level of integration, but 2 of those terms cancel out on the lower end, or actually go to 0 on the lower end, leaving 6 terms. But it's actually better than that, because out of those 6 terms, there's only really 3 which are important. This is the hole type. The only one of these 3 terms which is important is this guy right here. When phi is negative, this becomes positive. So in accumulation, this becomes dominant. These terms are clearly 0 in accumulation. In depletion, a little bit of depletion, this term predominates, but as the depletion increases, this term starts to come to life. Now, we can take the Q and just differentiate it to get the capacitance. The capacitance is, by definition, if it's a simple parallel capacitor, it's just Q divided by voltage. If it is a situation where Q varies with voltage, then we use the first derivative, and that's what we have here, dQ dphi. Well, we know Q as a function of phi, so we differentiate it. Well, it's obviously, there's a bit of a mathematical bookkeeping issue here, but it really isn't all that bad. So we're differentiating this bad boy right here. We take out the constant, and we find that it is given by this expression right here. You can go through this. It's basically using the chain rule, because we have functions of phi, and then we have functions within functions. So we take, for example, we take this guy, we differentiate it, and that we get the minus 1/2. That's why we have the same term here, this term here. The minus 1/2 is in the denominator, and then we differentiate the numerator. And these 4 terms here are the derivative of the numerator. This term here is the 1 term. This term here is this term here. And of course, when we differentiate 1, we get 0. Same thing over here. So we get now 4 terms on the numerator, down from 6. And now we have to analyze this thing. Well, First, let's look at flatband. So flatband is conceptually very simple. All we do is you put in phi is equal to 0. Well, phi is equal to 0, this becomes 1. 1 minus 1 is 0. Phi is 0, this becomes 0. All this goes away. Same thing over here. This becomes plus 1. Minus 1 cancels. Phi is 0. 0. Everything is 0. Does that mean that the capacitance is 0? No. We have a problem. Okay. So that's what we have here. Vg is equal to V flatband. Phi is equal to 0. The surface number of holes is equal to A sub A. The surface number of electrons is equal to the n squared, ni squared over ni. So for 10 to the 17th, this is 10 to the 17th, and this surface number of electrons is 10 to the 3rd. So we have kind of a problem here. We know there's a capacitance at flatband. Oh gosh, it's up here. It's big. And yet this thing says it's 0. Yikes. What do we do? Well, at flatband, there are essentially no electrons. So all these, I should say, we're down to the capacitance here. These two terms go to 0. So that's fine. And that's true in the numerator also, denominator, excuse me. So we get rid of this, and we get rid of this, and now we concentrate on these terms right here. We have 2 terms in the numerator and 3 terms in the denominator, and what we're going to do is expand the exponentials. So that's what we do. We expand the exponentials, both in the numerator and in the denominator. The 2 terms in the numerator and the 3 terms in the denominator. What are we expanding? Well, we're expanding the exponentials. Obviously, you don't expand 1, 1 is 1, and we don't have to worry about the beta phi. We're not expanding that. This term we expand, and this term we expand. And we find when we do that, we still get 0. Yikes! So, if we have just a 1-term expansion, 1 plus x, and you can see that right away, if you expand the 1 plus x here, you get minus 1 plus 1. That's the x term, and that's not good. So what do? We have to use the next term, the x squared over 2. So we do a 3-term expansion. And if that didn't work, oh my goodness, we would try a 4-term expansion. Whew. Hopefully we won't have to do that, and in fact we don't have to do that. So we use now a 3-term expansion. Let's see how that goes. Actually, let me correct that. That's not exactly true what I said. 2 terms are good enough in the numerator. 2 terms are good enough in the numerator, but not in the denominator. So in the numerator, we're fine. In the denominator, we are not fine. Notice the numerator would be 1 plus x with a minus sign. X is beta phi. So you can see that the minus 1 cancels out with the plus 1, and the minus beta phi becomes plus beta phi because of this minus. So that's fine. So we get a nice term in the numerator, just Na times beta phi. The Na is right here. It does not work in the numerator. So you notice the numerator has 1, 2, 3 terms for the expansion, plus the other 2 terms, minus 1 plus beta phi. Those are these terms. This is the expansion of the exponential, and these are the other 2 terms which are left over. The beta phi's cancel out, the 1's cancel out, and we have a square term. And then we just do the algebra, and we find that C sub s is equal to, or given by, equation 1833. We put in beta. Beta is Q over KT. So I remember the Q here because we're going to need it. And this is the expression for the capacitance at flatband, otherwise known as the flatband capacitance. Well, it looks not very intimidating. Actually, it's rather simple. But what in heaven's name does it mean? Well, let's put it into a form which is more useful. The capacitance, by definition, the areal capacitance, is given by the permittivity divided by the width of, or the distance between the two electrodes. In this case, the T-ox. So, we're going to take this guy and we're going to pull out an permittivity, and then we're going to divide by what's left over. So if you take this and you essentially do the algebra, you get back to here. But this is the form we wanted. Permittivity divided by some, length. Well, yes. Is this a length? Actually, it is. And we're going to show that right now. And it's a very special length. And here is the units. We always go back to units. I put the 2 question marks because we don't know. We're going to test it out, see if it really is a length. Oh, it's under the square root sign. The permittivity is in farads per centimeter. KT divided by Q is in joules. And KT is joules. Yeah, KT over Q is energy electron volts. Boy, am I sloppy. But just KT is energy in joules. And then we have Coulomb squared because we have Q squared. And then, of course, NA is just number per cubic centimeter. In this case, holes per cubic centimeter. So the units are centimeters to the minus 3. And then we take a farad. A farad is Coulomb squared per joule. Put the rest of this stuff down. Joule, this joule here is this joule. Coulomb squared, Coulomb squared. And let's see. Oh, the centimeter here is on the bottom. But here we have centimeter minus 3 on top, which gives centimeter to the minus 2 in the denominator, or centimeters squared on top. Either way is fine. I can make it centimeters to the minus 2 on the denominator, or I could have put it at centimeters squared in the numerator. The joules cancel out, the Coulomb squared cancel out, and wow, that's amazing. I get centimeters. Who would have thought this gunk here is centimeters? Well, it makes sense because it has to be centimeters. An areal capacitance is permittivity divided by centimeters. This is a relatively interesting quantity, and this is actually called the Debye length. How cool is that? Okay, so we have conquered the flat band, and now let's go on to threshold. So a threshold, Vg is equal to the threshold voltage, the potential, the band's been down, and the potential is plus 2 phi b. Bending down is positive. The surface number of holes is P0, which is n sub a, 10 to the 17th, but it is severely compromised by that minus 2 phi b. So basically P sub s is zip. It's 10 to the 3rd, and it's just not important. And 0, the equilibrium number of electrons, is also 10 to the 3rd. So these two values are precisely the same, 10 to the 3rd, and we'll neglect them. This is the guy that dominates because it's 10 to the 3rd multiplied by this huge exponential, and the surface number of electrons then is 10 to the 17th, equal to n sub a. So now we'll go back to our original equation, and we'll put all this good stuff in there, and let's see what happens. Well, P0 times this exponential, the phi is now 2 phi b, not too big. This is going to go away. P0 times 1 is n sub a. I didn't actually write down the P0, but the P0 is n sub a. So we have, that's where this comes from. N0 times the exponential is also n sub a. That's this one right here. Surface number of electrons at the interface is equal to n sub a. And of course, n sub 0 is really small. So this term goes away. This term is n sub a. This term goes away. And this term, the plus 1, is also n sub a. Okay, so let's see what happens now to the denominator. Same thing. Whenever we have P0 multiplied by a minus exponential, goes away. P0 times minus 1 is n sub a. Here we have n sub a, that's the P0, multiplied by beta times phi. Phi is 2 times the bulk potential. So this term here becomes this term. So 1, 2, 3 become 1, 2, 3. Minus n0, that's the last term here. That clearly goes away. And let's see. This term certainly comes to light because this is n0 times e to the 2 times the bulk potential. So this first term here is here. This is big. What is it? It's m sub a. And this term is essentially 0 because it's puny. This term is finite, but this term is so small, so we don't have to worry about that. So we get, from these three terms, we get two terms. First term and the last term. And now we see if we can cancel these guys out. This is just basically what we had before. And if we look at the numerator, we have two NAs. This guy, of course, is Zippo, so we don't have to worry about that. Likewise, for the denominator, this is 1, 2, 3, 4, 5, but it's 0, so let's say 1, 2, 3, 4, 5. Clearly, I don't have to worry about that. This guy is P0. That's this one. This one is n sub a, which is also P0. So this cancels with that. Actually, that's good because I guess the NAs, the N zeros would cancel. They're small anyway. I don't know why, but to be precise, we cancel those out. So I guess it's a good idea to carry that along. And we just have one term. There it is. 2 beta times the bulk potential times n sub a. Substitute those in. We have 2n sub a on top. We have denominator is given here, and we just use some algebra, and we arrive at the areal capacitance at threshold. So this is the region in this dotted, I guess it's green area. I've taken the liberty of moving this over a little bit because really what we're interested in is the region from the edge of the depletion region into the bulk. And this region in length, we're going to see, is extremely narrow, on the order of tens of angstroms, perhaps 100, 150 angstroms at the most. But it's a very important region. And this is where the Debye length will come in. So traditionally, this is what we had. We have a depletion region, and we have a bulk or quasi-neutral region. Let's start with the quasi-neutral region first. Here we have a density, charge density of 0. It is neutral. And the reason it's neutral is because even though, let's say, again, our doping is 10 to the 17th, in this case, it is donor doped, it's ND, and the fixed ions are positive, so we have 10 to the 17th fixed ions throughout this region. They're not moving anyplace, but they're covered, quote unquote, by 10 to the 17th free electrons. So the net charge is precisely 0. Now, if you want to be very precise, there are about 10 to the 10th thermal electrons and 10 to the 10th thermal holes, but we disregard those for now because they're so minuscule compared to the electrons and the non-thermal electrons and the fixed ions. In the depletion approximation, the depletion region is depleted of those electrons, and the only thing we have essentially are the fixed ions, and therefore we do have a charge density of 10 to the 17th positive. So if I was going to label this, I probably should, this ND plus would be 10 to the 17th per cubic centimeters. So I suppose we need to emphasize this particular picture where we go from 0 to 10 to the 17th in a infinitely thin layer here. There's a spike or a delta function or just a immediate transition, almost like a metal. This is not the accurate description. This is a description that we use mostly in undergraduate courses, but our job here is to modify that for the real world. And the depletion approximation contends that the charge density rho abruptly changes at the boundary. Well, in the real world, that just doesn't happen. So in the real world, if we take a look at this region here, we have a transition region where the charge density goes from ND to 0 in a length of LD. And our job is to find out what LD is. So that's what we're going to do. So now we really have three regions. We have the depletion region, we have the transition region, and we have the bulk region. So let's kind of reason this thing out. Here we have every single fixed ion covered by an electron. Now we get to this point right here, and we start to go into this transition region. So a couple of atoms in, maybe 2, 3, 4 angstroms in, we have all of the fixed ions except a couple. There's a couple fixed ions that are not covered. So there starts to be a positive charge density because ND is positive. We go a little bit more. Well, then a few more ions, fixed ions, are uncovered. And a few more, and a few more, and a few more. And as we go further and further in, more and more of the fixed ions become uncovered until we get right to this point right here, the edge, and then 10 to the 17th are uncovered. So that's the idea. We expect it's going to be exponentially increasing because here it's extremely small, and then not all of a sudden, but as it gets closer and closer to the depletion region edge, the numbers just shoot up very dramatically. So that's the idea. So we look at rho, the charge density, and we say it's the number of fixed ions minus the number of electrons. Now, if the number of electrons is equal to the number of fixed ions, clearly rho is 0. That's out here. if the number of electrons is essentially 0, I say essentially 10 to the 10th, only thermal, then rho is 10 to the 17th. And that, of course, is right here. Now we just put that into Poisson's equation, where now n is a function of x. So we have an equation, a second-order differential equation in the variable x, and that is what we have to solve. We expect that the solution will be exponential. Okay, so we start at the bulk. Why not? In the bulk, as far as energy goes, it's the E sub f minus E sub b, because this is n dope, so the Fermi level is above E sub I. How much above? 10 to the 17th, it's 0.42 eV. And as far as potential goes, I put the Q in. Hooray for me. This is P bulk will be 0.42. Now the number of free electrons will be equal to the intrinsic value multiplied by E sub f minus E sub I. Now of course if E sub I, if E sub f minus E sub I is 0.42, 10 to the 17th. However, E sub I ain't this difference here is not 0.42 in the transition region. It's only 0.42 in the depletion region. In the bulk region, it's of course 0. So in the transition region, 1843 is our starting point, and that's basically just what I said here. In the depletion region, in the depletion region, E sub f is equal to E sub I, and of course n is just n sub I, and that's exactly what we would expect. That's nothing very earth-shattering there. Okay. And this is figure 18.7, which basically just says the same thing. In the bulk region, we have a nice value of 0.42. The Fermi level is above E sub I. Bands always bend up for N-type silicon. And this is the region that will be of interest, is the transition region. And what you notice at the beginning of the transition region, this bending is extremely small. It only gets large when we get very close to the Fermi region, so Fermi level. So really one can say, oh my goodness, maybe we're not very accurate here because we're going to make an approximation. But you know what? We'll live with it and we'll just see where it goes. So in the, again, the Poisson's equation in the transition region is 1845. And sometimes, again, I forget the minus sign or I'm too sloppy to put it in, but I realize that I need it, so I do put it in this region, in this equation here. So if you get the wrong answer, if it's negative, guess what? You forgot a minus sign. So that's just my take. Anyway, this is the critical issue right here, that the electric field is very small in the transition region. The band bending is very, very small. Certainly in this region, not a problem. As we get over to here, maybe a bit of a problem. Okay, so it means that the electric field is very small in the, the electric field is very small, which means that the phi dx is very small in the transition region. Now it's just turning the crank. So 1846 basically says, let's consider that the intrinsic level, which we know is going to change, it's a function of x, and it's going to bend up, and it's equal to the bulk intrinsic level minus some itsy-bitsy little amount, a delta. And the last line, we convert from energy to potential. And that's why this guy here, EF minus EI, is V sub B, and the delta E sub I is a delta sub V. And this is the important thing right here, the delta phi. So we converted from energies over here to potentials over here. And we do that, we flip it, and that's always the case when energy and potential are mirror images one of another. So this is what we're looking for, this delta phi sub x, extremely small at the start of the transition region and gets not so small as we move over into the depletion region. And notice that x is measured from left to right in this particular case. So in 1847, and we're just continuing to turn the crank, we write down what we had back here for n. That is all of this right here. And we notice that the first term, n sub I e to the q phi b over kt, is just nd. That's pretty straightforward. We have minus nd over here. This term just comes down. So we remove the nd, and we have equation 1847. Okay. Since, 1848 just says by definition, n sub d is n sub I e to the ef minus ei divided by kt, or n sub I e to the q, I remember the q, good for me, bulk potential divided by kt. Now here is another one of our critical issues. We can, if this thing is very small, if phi is small, this guy is really small, and we expand it to one term. We don't have to do two terms like we did when we were finding the flat band voltage. Just one term, e to the minus x is 1 minus x. So that's exactly what we have in 1849. And we just put that in to our equation here. And we immediately, the ones cancel out. This one cancels with that one, and we get equation 1850, which is a second order equation in delta phi. Phi is composed of two parts. It's a constant part plus the delta phi, and of course the constant part, the first derivative, as well as the second derivative, will be 0, which is phi sub b. So finally, we have equation 1851 immediately moves down to equation 1852, and this is a very straightforward equation. To solve, it has the form of d squared y dx squared is equal to cy, where all this is your c, and y, of course, is delta phi, and the solution involves two constants, c1 and c2, and C2 is just our Debye length, and that's what's sitting right here. So we should be really happy. We have the solution, sits right here. We have the Debye length, which we found in a different technique for the flat band voltage, but here we're finding it in a much more, say, sophisticated way. But we still don't have the numerical. We can't evaluate this because we don't know what C1 is. So in order to get a real number on what's going on, and we want to numerically evaluate it, we need to know what C1 is. Well, this equation is, or the solution is a potential. Now, this term is unitless, as it must be. It's a length divided by the length, always true. We can't have units on exponentials. This is unitless, but the solution has units of potential. So we expect that C1 will have units of potential, and the question is, what do we pick for C1? Okay, well, a reasonable choice for C1 will be just the bulk potential. Now, why should that be? Because when x is equal to the Debye length, let's go all the way back to here. So for at this point, which is in the bulk, where x is equal to the Debye length, then what do we have for the potential? Well, we would hope that it would be, I should say not the potential, the delta phi. would expect the delta phi would be 0, because we're in the bulk. There is no change in potential in the bulk. So V sub B looks like a good value, because at the edge of the transition region, between the transition region and the bulk, the delta phi would be 0. On the other hand, when x is equal to 0, we would expect the delta phi would be equal to the bulk potential. And this equation satisfies both of those boundary conditions at either end of the transition region. So this is a reasonably good choice for C1. So on with that knowledge, now we can actually get some more numerical values. However, before we do that, a little bit of a problem, as everybody knows. I'm kind of sloppy sometimes with my signs, and I want to go back here and correct something. I had the X arrow going from left to right, which is the normal way to do it. In this particular case, however, X goes from right to left. So this is X equals 0, and this is X equals LD, the demarcation between the transition region and the depletion region. Now, if I had half a brain, I would have put the transition region on the left side of the depletion region, and then everything would have been hunky-dory, because in that case the X would have gone from left to right. But we've seen X's going from right to left all the time in the BJT, so it shouldn't be surprising. So this is going to make things work out really the way they should work out. So here's the point. If the sample is doped 10 to the 17th, that's our default doping, at the demarcation between the transition and the depletion region, right here, X is equal to LD, and I put that in right here, and this becomes e to the minus 1, because X is equal to LD, and I get that this term in parentheses is 1 minus e to the minus 1, or 0.632, and therefore I can get the phi immediately by multiplying by the bulk potential. It's equal to 0.266. So what is, well, if it was 0.42, it would be 10 to the 17th. 0.266, I can easily find out what that is just by putting in that value for e sub f minus e sub I, and I get 10 to the 14th, 3 times 10 to the 14th. So what that tells me is I start out at potential equals 0, the charge density equal to 0, and by the time I get to this point right here, it is about 3 times 10 to the 14th, and as soon as I go just a couple of atomic lengths into the depletion region, it immediately goes up to 10 to the 17th, another 3 orders of magnitude. So it goes 4 orders of magnitude from here to here, and another 3 orders of magnitude, because it's exponential, goes up very quickly when it gets into the depletion region. So that's what we have there. And that transition from the bulk into the depletion occurs in about 100 angstroms. And we'll see that just a little bit when we calculate the length of the bi length. Okay, so in fact that's what we're going to do right now. First, this is kind of a repeat. We found that this is the bi length, and we did this previously. I'm just repeating the calculation. In this particular case, we're going to use MKS units. So everything is in joules, length and other, not centimeters, but meters. The permittivity is in coulombs. This is coulombs per, I think it's what, coulombs per Newton. I'm not sure anyway, but this is the units, And we cancel everything out. Joules, of course, is a Newton meter, meters cubed. And, of course, this is Q squared. So everything that's left over, Coulomb squared divided by Newton's, would be the permittivity, I believe. You can check that. But anyway, important thing is we get the Debye length is equal to meters. And that is exactly what we expected. So we put the numbers in, and here's where using MKS is going to be a little bit perhaps strange. So the permittivity is about 10 to the minus 10th for silicon, and KT is in joules, so it's 4.110 to the minus 21. I think we've seen that before, way back when. Coulombs don't change, and N sub D, instead of 10 to the 17th, which is 10 to the 17th per cubic centimeters, it's 10 to the 17th cubic centimeters per cubic meter, which is 10 to the 6th. So at 10 to the 6th times 10 to the 17th, which is 10 to the 23rd, and when the dust settles, we get about 127 angstroms, and that's a reasonable value for the Debye length, on the order of 100 angstroms. However, as we're going to see, we have the Debye length whenever there is a transition from a bulk region or neutral region to a region which has fixed charges or charges that don't move. That happens in the plasmas, and it also happens in outer space. So in plasmas, we'll find the Debye lengths are not measured in tens of angstroms, but in centimeters or fractions of a centimeter, and in outer space, it can be many, many meters. Well, in our study of semiconductors and semiconductor devices, semiconductor materials, we have lots of lengths. Two of the lengths that we've really been concentrating on are the depletion width, W, and here it's rather hopefully familiar equation. This is a non-equilibrium equation. There's applied voltage, but the important thing is it's 2 epsilon times some barrier, either an equilibrium or not an equilibrium, forward bias, reverse bias, doesn't matter. There's some barrier divided by Q times the doping. This is the Debye length. Let's compare these two, and you'll notice that the Debye length does not contain a barrier. There's no barrier in the transition region, so that makes sense. But if there's no barrier, in order for this thing to be a length, we've got to worry about units. Well, the barrier is in energy, KT. So that's why we have a KT in the Debye length. So that makes sense. If we don't have a barrier potential or barrier energy, we better have some energy. And what better energy to put in than KT? So if we associate the barrier with KT, these things are really very similar. And we can almost, I should say KT over Q, because it's measured in volts. And that's why we have volts up here. So the point is that if we have equal dopings and we have reasonable barriers, we would expect, and what's a reasonable barrier, 1 to 3 volts, or for example, for a applied voltage, we would expect the ratio of the depletion region to the Debye length to be more or less constant at about 10 to 1. So if the Debye length is 100 angstroms, 100 times 10 would be 1,000 angstroms. And that's exactly what we find for a high doping of 10 to the 17th. If the doping was 10 to the 15th, that ratio of 10 to 1 would carry over. And so instead of being 100 angstroms, this would be, well, a fair bit more, depending on what N sub D. The lower the N sub D, the higher the Debye length. The lower the N sub D, the higher the depletion region, such that the ratio is on the order of 10 to 1. And then we just put in some numbers, and you can do this with putting in numbers yourself and find that ratio it makes sense. And it's got to make sense, because the Debye length, we expect that it will be quite a bit less than the depletion region. If the Debye length ever became equal or greater than the depletion region, that would be really, really strange and non-intuitive. So it's nice that we have this nice ratio of about 10 to 1. So I won't go through this in any detail. What I do here is I give an analogy to a plasma. So a plasma is an uncharged gas, and in the plasma itself, it's like the bulk. There is no net charge. However, near surfaces, and I have a fetish, I guess you'd say, towards plasmas, because I worked in them both in theory and in practice for quite a number of years. So, excuse me. Whenever we have a surface, like a wall of a reactive ion chamber or something like that, then we have a region which is depleted of charge. And there is a transition region between the charge region near the wall and the plasma itself, and that's called the dark region. And so we say, okay, there's an analogy between plasmas and semiconductors. So what's the analogy of ND? Well, that would be the charge density in the plasma. Well, plasmas are not solids, they're gases. So ND is many, many, many orders of magnitude lower than what we have in a solid semiconductor, and therefore the LD is many orders of magnitude greater, and that's why the Debye length for plasmas is on the order of centimeters, where for the Debye length for semiconductors is in the order of tens of angstroms. So you can go through and read about that. And let's we've come to the end of our MOS, and we're going to celebrate now with a clip from the finale of the wonderful Mozart Flute and Harp Concerto, Köchel 299. We're going to listen to, I think it's Michael Tilson Thomas as the conductor, and James Galway on flute, and Marisa Riblis on harp. Enjoy, and we'll see you next time when we start on the MOSFET.